Okay, welcome to Screencast 13. This is the first in a series of 2 screencasts discussing topic 4, which is catalysts. Okay, so the objectives are listed here. We're going to address the first objective in this screencast, which talks about comparing the modes of action of homogeneous and heterogeneous catalysts. Okay, so before we jump into that, do want to refresh your memory on what a catalyst is and how exactly it works. Okay. So a catalyst is simply a substance that increases the rate of a chemical reaction without itself undergoing any permanent chemical change. Okay, and so this phrase increases the rate is important. Remember that the way a catalyst works, especially when we're talking about reactants and products that are in equilibrium with one another, say I have A plus B in equilibrium with C, okay, the actual amount of C that you can possibly make from A and B is not affected by a catalyst. What it does do is increases the rate of your ability to form C from A and B. Okay, and remember the way it does that, if we look at our sort of energy level diagrams, remember these things, guys? Okay, so what a catalyst does is it lowers this activation energy. Remember this value here is my activation energy. And so the catalyst allows that to be lower, which allows you to sort of get over the hump easier. And therefore, that increases our rate of reaction. I thought this was cute. In one of the textbook I was using, it says the Mandarin word for catalyst is somei, which means marriage broker. Okay, so a catalyst is kind of a vehicle that you can put into your reaction to help A and B come together to form C. Okay, so regardless of what type of catalyst you're using, whether heterogeneous or homogeneous, the main benefits of catalysts are listed here. So one of the main ones is that lower temperatures are needed, usually to increase the rate of a reaction. Temperature is definitely one knob you can turn, and so it allows you to run under lower temperatures. And this applies to pressure, lower pressures as well, if you are dealing with gases as your reactants. The other nice benefit of a catalyst is if you have competing reactions going on with 2 reactants, say you have A plus B, and you could either make C from that, or you could make D. Imagine these are in equilibrium. Okay, a catalyst can help you form one of those products over the other, and so that's a nice benefit of them as well. Okay, so let's just refresh your memory on the 2 different types of catalysts and how they differ. The first one is a homogeneous catalyst, and so this is going to be a catalyst that exists in the same state of matter as the reactants. Okay, and so usually this is in some kind of solution. So if you have a catalyst, your reactants are usually going to be in some kind of aqueous solution. So in this picture, you can the sort of tan background is your solvent, and the blue and yellow species are your reactants, and then the green is your product, and then the red is your catalyst. Okay, and so they all exist in solution together, and so each of your individual catalyst molecules can sort of mediate that reaction between the blue and yellow particles to occur. This is in contrast to a heterogeneous catalyst, which is always going to be in some kind of different state of matter. The catalyst is usually some kind of solid, and then the reactants are either going to be liquids or aqueous solutions, okay, or gases. Okay, so just like before, the yellow and the blue are going to be our reactants, and then they can interact with the catalyst surface and produce products. Okay, so the mode of action, remember that's the main objective for the screencast, sort of how they work, okay? If your catalyst is homogeneous, okay, usually what happens is that the catalyst will react in one step of your mechanism and then is regenerated in a later step, okay? And so remember, especially for HL, we talked about different reaction mechanisms. The catalyst will participate in that reaction mechanism, but by the end of the mechanism, the catalyst itself is regenerated, and so it's not used up. And here's just one example of a homogeneous catalyst system. I'm going to try to find others. I know there probably are, and I just couldn't think of them as I was making the screencast. But the reaction certainly between a carboxylic acid and an alcohol to make an ester and water is one system that uses a homogeneous catalyst, and that catalyst is usually sulfuric acid, which is really the H plus in that sulfuric acid that is acting as the catalyst in this system. Okay, so this is one good example, and like I said, I'm going to try to find more for you, especially since this one is sort of this is one that HL is familiar with, but SL is not. Okay, so now let's talk about the heterogeneous catalysts and how they work. So what the catalyst does in this case is it provides a surface upon which the reaction can occur. And there's really two benefits of this. First of all, the fact that these reactants will in some way attach themselves to the surface, it allows the surface to help orient the reactants, and so they're more likely to collide with some kind of correct geometry. And that, if you remember from collision theory, that's one way in which we can speed up a reaction. Okay. In addition, when those reactants bind to the surface, that can also weaken the bonds within the reactants, and then that makes them more likely to react as well. So these two key features are ones that you're going to want to keep in mind as you're thinking about how a heterogeneous system works. Okay, now for heterogeneous reactions, there's plenty of more examples that certainly came to mind as I was thinking about this. Okay, so these first two are from the equilibrium unit. Remember, this one is the contact process, which is involved in making sulfuric acid. Okay, so once we make the sulfur trioxide, that in turn can react further to make H2SO4. And so this reaction, the catalyst for it is actually a gas. Oh wait, that doesn't make any sense. I don't think this is right. I think this is a solid, guys. And I'll confirm that. I don't know why it says gas here. So SO2 and O2 will react on the surface of V2O5. Likewise, remember this reaction, this is the Haber process, which we spent a ton of time talking about for making ammonia, which goes into the production of fertilizer. Iron is our catalyst for that reaction. Once again, heterogeneous, because this is a solid, the reactants are gas. And then finally, this from the organic unit, this is an alkene. And alkenes will undergo a hydrogenation reaction of alkenes. The catalyst in that case is nickel. Okay, so these are three good examples to keep in mind as you're thinking about examples of heterogeneous reactions. Okay, so that concludes this first screencast. In the next screencast, we're going to be talking about advantages and disadvantages of heterogeneous versus homogeneous catalysts, and we'll talk about how you go about selecting a catalyst. Let's go ahead and stop there. Okay, welcome to screencast 14. This is the second in a series of two screencasts on catalysts, and we're hitting these second and third bullet points down here, these objectives for catalysts. We're going to look at advantages and disadvantages of one over the other, and talk about what factors you need to consider when you're choosing a catalyst for a particular system. Okay, so let's just talk about sort of advantages, disadvantages first, and we'll focus on homogeneous catalysts. The big benefit for homogeneous catalysts is that they're much more efficient than a heterogeneous system. And so for that to make sense, you need to think about what a homogeneous catalyst looks like. If you think of that picture from the last screencast, you actually have individual molecules that each can serve as a catalyst site for particular reactions. And this is very different than, say, a heterogeneous system where you might have a big surface where those reactions can only take place on the outer edge of the surface. So gram per gram, or mole per mole if you want to think of it that way, heterogeneous systems just have a lot more sort of bang for their buck because you can use because it's homogeneous, each little individual molecule can act as a catalyst site. However, there are some significant disadvantages to homogeneous systems, and the main one is the that they can be very difficult to separate from the product. So remember, you're adding it, so if we think of an aqueous system where you're adding this catalyst and dissolving it in water along with your reactants and your products, at the end of the day you need to get that catalyst away, or get your products away from the mixture. And so you usually end up using distillation to sort of distill off your products and get it away from the catalyst. And so that can be pretty expensive because you've got to add a lot of heat, a lot of energy to that system. And then recycle your streams that have the catalyst in it, and it gets quite complicated. The other disadvantage is that the homogeneous catalysts, there's only so many of them available. There is a lot of research looking at the development of new homogeneous catalysts for various reactions, but that research effort can be quite expensive, and so that's an issue with these homogeneous systems. So now let's take a look at heterogeneous. The big benefit is just sort of ease of use, in the sense that once you're done with the reaction, it's pretty easy to separate that catalyst from your reactants and products. And if you're lucky and you're using, say, a solid catalyst with a gas system, you can usually set it up as a continuous process where you just sort of run those gases. Say you have your catalyst here, you just run your gases over that catalyst, and miraculously your products end up coming out the back end. And so you can make quite simple and inexpensive reactor systems for these heterogeneous catalysts. However, there are disadvantages, and one of them is the one I just mentioned on the previous slide. These are less efficient. The reaction's only effective on the surface of the catalyst and not in the whole sort of bulk of the material. You can minimize that effect by increasing surface area, and usually what happens here is you might have, say, a catalyst that's really reactive. You might make it really small particles and then sort of coat those particles on the surface of something that is not the catalyst, which is usually cheaper. So that allows you to sort of get the most bang for your buck for that solid material. Okay. The other issue is that you can get poisoning of your catalyst, and so we'll talk about this in a later slide, but essentially you get some substance that binds to the catalyst and causes it to be inactive. And so this essentially uses up a lot of your catalysts. Many of these catalysts are made from expensive metals. So you've spent a ton of money on platinum, and then it gets poisoned, can't use it anymore. That's a lot of money down the drain. Okay, so those are sort of main advantages and disadvantages. Now let's talk about what you need to think about when you're trying to select a catalyst, and those are listed here. I have selectivity, efficiency, ability to function under the conditions of the reaction, the poisoning, which I kind of mentioned before, and you also need to consider environmental effects. So there's really 5 factors here. Well, let's just quickly go through each one in turn. Okay, so what do I mean by selectivity? Well, I think this example here really illustrates it well. Okay, so say I have a starting material, so this is my reactant, and this is called ethyne. It's a functional group we haven't really talked about, but it's basically has a carbon-carbon triple bond here. And it turns out that depending on how you react ethyne, you can get 2 possible products. I can either make an alkene from this alkyne, or I can make an alkane from this alkyne. Okay, and if you run this, in the absence of a catalyst, you would probably get a mixture of these 2. Okay, so what happens here is, depending on which catalyst you choose, I can either use platinum if I want the alkane, or I can use palladium if I want the alkene. Okay, and so you can see the choice of catalyst will preferentially select the product that you want. Okay, we also need to consider efficiency of the catalyst, and that's really defined by 2 factors: turnover number and turnover frequency. Okay, and so the definition of these are listed here. Turnover number is simply how many reactant molecules can be converted to products by the catalyst molecule itself. And so this is usually some number that is kind of a measure of how long that catalyst lasts before it just dies and isn't effective anymore. So you want this number to be as high as possible. The other factor you need to consider is turnover frequency, is how fast that catalyst can generate the product. Okay, and so once again, this is essentially a measure of rate. And so you want this to be as high as well, okay? So a lot of times maybe you'll go higher in temperature to increase your turnover frequency, but that might lower your turnover number. You're definitely usually fighting a balance between these two. Okay, so the third thing to consider is what conditions is that reaction going to run under with your particular catalyst, okay? And so a lot of reactions have to run under pretty severe conditions, even in the presence of a catalyst, which is supposed to allow you to run under milder conditions. And you need to make sure that the catalyst that you're choosing is going to hold up for as long as possible under those conditions without losing its efficiency, okay? So you want the catalyst to be really robust, to hold up. Okay, fourth effect is this environmental impact effect. And so the main catalysts you want to be thinking about when you're talking about the environment are uses of heavy metals or uses of strong acids or bases as your catalyst. So these are really common catalysts that you might see. Heavy metals are used both in heterogeneous and homogeneous systems. And those are toxic, so you definitely don't want to release those to the environment. Strong acids and bases are usually only used under homogeneous. So you want to, they can definitely end up in sort of the waste stream of your particular process, and you need to make sure that those aren't released into the waterways without being treated because it's harmful to biological systems. And then the final effect that you need to keep in mind is this idea of poisoning, which I kind of hinted at earlier. So here's our sort of formal definition of what poisoning is. The reaction of your catalyst with either impurities or other substances that cause the catalyst to become inactive. Okay, and how this usually happens is that catalyst will, these impurities will irreversibly bind to the active site on your catalyst and makes it essentially inactive. Okay, there's a couple different ways you can minimize this. You can either remove the impurities by purifying your reactants before you use them, or sometimes increasing the surface area of your catalyst essentially gives you a ton more active sites, and so then when it takes longer to essentially poison it so much that you can't use the catalyst anymore. But the susceptibility of a catalyst to poisoning is definitely one thing you want to consider. Okay. So those are the sort of 5 things you need to keep in mind: poisoning, environmental impact, the conditions under which that reaction runs, efficiency of your catalyst, and selectivity. These all feed into essentially the cost of running the process. And you want to be minimizing that cost, whether it's minimizing it by reducing poisoning, which allows you to use have to replace your catalyst less often, less hassles in terms of dealing with the environmental impact of your process, being able to run your process under lower conditions, or having that catalyst just simply be more robust. Efficiency, like I said, and selectivity is critical. Okay, so that short topic here, that wraps up our discussion on catalysts. So go ahead and take a shot at the questions in the worksheet packet. Let's go ahead and stop there.